you.
It's okay.
All right. So let me just give a brief explanation on how the assignment is. Then we'll continue. Now, the first question says that uh, suppose the insurer, that's a life insurance, is written on husband and wife, right?
Mm-hmm.
And suppose the insurer is interested in whether one or both of the members
Mm-hmm.
of the couple die in the next year, then the insurance uh, company must start by considering out the following outcomes. We say DH, which is death of the husband, or SH, which is survival of the husband. D there stands for the death of the husband. Then S there stands for survival of the husband. Then can you help us and project the assignment so that will be
In fact, I put the assignment on my phone because you started, because I was on the computer before, so I didn't even.
okay.
It was on my phone so that I can have a full screen for my class. That was why I didn't open it on my laptop.
Okay. All
But
right. So let me
you
just.
want me to read the question? Well, you're already there. The
Okay.
first question is, what
I
is
don't
the
know
total?
whether Mr. Osang has it, so that's why am.
Oh,
No, I don't. I don't.
there's a
Okay.
link sent to us, sir. Mr. Sir,
There-
there's a link sent to the
There's a
group.
link. Yes.
Yeah. So if you go there, you will see it. That's where I went to anyway.
So
Okay,
all
just
the
hold.
assignments.
Sorry?
Okay. Come again, sir.
Hello?
Hello, Mr. Osang. It's like he said something, right?
It's muted.
Okay. So
Oh, even dropped.
okay. All right. So let's discuss the assignment then before
Yeah.
we.
Yeah, please.
So we now have we we have DH, which stands for death of the husband. We have
Yeah.
SH, which stands for survival of the
Survivor.
husband.
Yeah.
We have DW, which stands for death of the wife.
Mm-hmm.
Then we have SW, which stands for survival of the wife.
For the world.
Yes. Now you know that this insurance company wrote the policy to insure both the husband and the wife.
Yes.
Now, so if that's the case, which means we are considering a pair to describe one of our outcomes. Do you understand?
Mm-hmm.
By pair, what I mean is that we are considering, because the insurance is both on the husband and the wife. So what we do is that we will compare either the husband dies or the wife survives. Do you understand?
Mm-hmm.
We'll consider either the husband dies or the wife survives. Because you know it is either the husband dies and the wife survive, or the wife dies and the husband survive, or the husband survive and the wife survive, or the husband dies and the wife dies.
Mm-hmm.
So you see, these are the peers. These are the peers.
So if you're writing it,
So
are
now,
you going to say interset or union?
okay, no, this is just simple because we are looking for sample space now.
Yeah.
So we now say our sample space is equals. We will now open the curly bracket.
Yes, that's why I open, but I only put
Then
DHW.
then our first pair will be death of husband and survival of wife. Then we'll enclose it in a bracket. Then we'll put comma. Then the second pair will be death of husband or death of wife. Then we'll close the bracket again. We'll put another comma. Then our next option will be survival of husband and survival of wife. Then we'll close the bracket. Then we'll put
So
another
there's
comma.
no intersection or union between them, no.
No, there's no intersection. We're just looking for sample space first.
So it will be
Then
DHSW
mhm,
bracket close,
mhm.
comma. Is
Then
that
DH. Yeah, yes. Go ahead.
SW?
Uh-huh.
Or another pair will be SH SH, hmm, yeah,
SHSW.
S, SHDW, something like that.
Yes, that's another option.
DW.
Then
Or,
we're going to have
oh, DHSH
uh
and D, DSH, DWS,
no,
D,
no,
D,
we can't have DHSH because that would be DH is death of
there will
husband
be no
and
survivor.
they are because if the husband dies, there's no how he will still survive. So we can't
Okay,
have
so,
DH. H there is for the husband.
oh,
So
so we,
we
so
can't
we
have
can have SHSW.
uh we can have SHSW, that's survival of husband and survival of wife.
Hmm.
Then we can have DHDW, that's death of husband, death of wife.
But I thought you said we should not consider. They said die in the next year. Correct.
That's the husband and wife different now. They are different now.
Oh, oh,
It is only when you say SHDH, that's when it's not an option.
SHDH.
Because
Oh,
that
okay, because the two cannot, it's mutually exclusive.
because yeah, exactly, they are mutually exclusive. They can't occur simultaneously
Yeah,
because
yeah,
the husband cannot dead and still cannot die and still be
yeah, and
alive.
still be alive. I got it. I got it
You
now.
got it now, ba?
Yeah,
Yeah.
yeah.
So that
Mr.
would be our
Osaho is back.
okay. Yeah, he has been back for a while now.
Okay.
Yes,
I don't know.
sorry, my network went off.
Yeah.
Oh, sorry about that.
Yes,
But are
Oh,
you with us?
yes, I'm with you.
okay.
Okay. So now that we've gotten the sample space, we can now go
Mm,
ahead to find the probability that the husband dies in the next year.
mhm.
Are we together?
Yes, but
All right. So
that the husband dies in the next year.
yes,
So is it the probability of
we are
husband
looking
die?
for that sample space now.
So
The
will it
sample
be
space will be H, that event, particular event.
whenever there is H or die,
Yes.
wherever
DH.
there is DH?
DH, we'll pick that one. We'll pick those
Okay.
ones. Anyone that has DH, we'll pick those ones.
Probability of DHSW,
Mm-hmm.
or where is DH again? DH and I have,
DW.
I've missed it. DH. Oh, I've
DW.
missed. I've there's no
All
so
right.
many
So,
survival.
if that's the case, it shows that we have understood that particular example a bit.
It's only three in the sample space.
So, it's up to four.
Eh.
It should be up to four.
Husband, death of husband,
Mm-hmm.
survival of wife.
Mm-hmm.
Okay, we should have death of husband and death of wife. Okay, yeah, I got it now.
You get it now, ba?
Hmm.
So, with this hint,
So we have the sample space, but you are saying we should look for what's it called? We are
the
looking for
sample space.
probability.
No, the sample space that the husband dies in the next year.
You didn't say something. You said what is the probability that the husband dies in the next year?
Eh,
Probability.
eh, okay. Yes, that's it now. So that will give us now. If you now you must for you to calculate that one, you must have the sample space for the husband now,
Okay,
the
so I
event
will
of the
have the
husband.
one for the one that I will pick is DHSW and DHDW.
uh Then the probability will now be what?
Oh, that's where.
DH the event of the husband all over the total sample space. We have given the formula now. Classical probability.
Oh, oh. So it's going to be, but it's two. You see, this is where I'm confused.
Two,
DH.
two over four now.
Oh, I got it. Uh-huh. Oh, so where because we now we say the whole thing in counting is equal to 4. So wherever
Yes.
the probability of husband death is next year, we could
Mm.
see it appearing in 2. So it's 2 over
Yes.
4.
Yes.
The
So
wife
that's
two.
the probability. So, I wanted to keep the answer so that once you solve, you will submit them. But now we have already said the answer. So, but just go and rewrite it in a
Proper way.
nice, proper format, yes, and then understand. Then we will now submit.
Okay, what about the hall? The hall is the union.
The what?
You say the probability of husband or wife
Yes.
dies in the next year.
Yeah, remember we did conditional probability. Remember,
And so,
we we gave formula for conditional probability. We say if there's an
probably,
and,
uh-huh.
we say if it is or, it means that you are summing. Remember something like that.
Oh,
Then we
husband
say
die or wife.
or wife. So
Wife
you sum.
dies. So,
Mhm.
so that would now make it wife die, husband die, husband die, death of husband, death of wife, death of husband. So that would be
It's still confusing now, but don't worry. Just by the time you sit down and look at it again, you will get more.
because the reason why the whole is like everything is one. It's 4/4.
Uh, it's still valid now. Probability cannot be more than one. If it is one,
Mhm.
then it's still it's
That's
still
why I
it's
was
still valid.
confused. So it's going to be 4/4, which is one. But the and meaning it's either husband and wife died in the nest. So die. So that's the occurrence of two. Die. Death of wife. That would be 3/4.
Well, we just do it first. Then when you finish doing it, we
And
can
so
we look at it.
we are writing it in numbers. That's what I'm even trying to say.
Okay,
Are
yeah,
we
yeah.
writing it in 1/4, 2/4? That's what I'm saying.
You don't want me to give all the answer.
No, like I said, I'm so confused that I
Okay.
know.
See what we're going to do. See what we're going to do. Everybody should just go back and let's redo it and submit before weekend. Then when we come
Okay,
to the next class, we'll now project the
okay,
whole
okay, okay.
work, and then we'll see what.
Yeah, okay. Thank you. But let's go to number two. I want to be a good student. See, that's why
Okay,
I'm trying to.
all
So,
right.
in order, 51% of the adults are male. One adult is randomly selected for a survey involving credit card usage. Find the parallel probability that the selected person is a female. Oh,
Find a what?
the pari probability that the selected
Prior
person,
prior prior probability.
yeah. So, but 51% of the adults are male. It shows
Mm.
that 49 will be female.
But have you did you actually go through the
I
last
did.
class?
I did.
What
In
do you
fact,
have do you have the PDF material for the last class?
the recorded one.
Oh, no. You are supposed to have the main PDF material. You don't download it from the
Oh, I
drive.
went through the recorded video.
Okay,
Mm.
okay. All right. See what we are going to do. Um, we will stop the discussion for the assignment now,
Okay,
and
and
then
start the class.
start the class. Then
It's just that okay,
we will make sure that all the materials are there in the drive so that we'll go there and look at them again.
and look at it. Okay, all
Yes,
right.
in PDF format so that we'll
Okay,
look at it and then we'll see because I'm sure there are similar examples there.
okay.
Yeah, so once we
Thank you
just
very
read,
much.
we can
Thank you
get.
so much.
Okay, it's all right.
Yeah. So we can start. Sorry. Okay.
Mr. Osao, we can start, right?
Yeah, we can.
All right. Just give me some moments. I'm trying to uh, connect my laptop. Coming, please. Just give me some moments, please. I'm coming. I'm having some issues with my laptop, but just give me like a minute. I'll sort it out. I'll be right back. All right. Can we all see my screen?
Yes, yes.
All right. Thank you very much. So we will start right away. This is probability theory and distribution, lecture 3. Uh, uh, my name is Anzaku Jacob Patrick, and we'll be taking the course with Ilyasu 80. So we're going to have in this presentation the outline. Then in the outline, we will have a recap of last lesson. Then we're going to talk about the moment generating functions, MGF, their properties, and their uses. We will also look at discrete probability distributions. We will look at the under the discrete probability distributions. We will look at the binomial distribution, the Poisson distribution, the discrete uniform distribution. That's if time permits. And then under the binomial distribution, we will look at some characteristics of the binomial distribution, uh, how to model the binomial distribution so that we understand what kind of behavior of random variable describes the binomial distribution or the binomial distribution. What kind of behavior does it describe? And then we look at the practical applications. We will also look at how to get the mean, which is the expectation of the binomial distribution, and also the variance. And then we'll look at some practical examples. So then we have the summary, then exercises, and then we will now conclude. So recap of our last lesson. So in our last class, we look at the conditional probability and the Bayes theorem. Under the conditional probability, we say that this is a probability, uh, we're looking for a probability given that an additional information has been given, which is a condition. And under that condition, we say there is what we call the prior probability. And we say the prior probability is when the additional information is given before we know it before. And then we also have the posterior probability, the information that we know after. We also look at the Bayes theorem in our last class, and we had the formula for the Bayes theorem. It helps us to calculate conditional probability, some scenarios, some special cases of conditional probability. We also look at the random variables. We say that because experiments happens randomly, that is why they are called random variables, and we don't know which value it may take. A variable is an event that we don't know which value, numerical value, it will take at which given time. So that's why it is a variable. It may vary. So a random variable is an event that occurs randomly. Now, also talked about the probability distribution, and in our last class, we said that when we hear of probability distribution, it actually describes the behavior of this random variable that we're talking about. From random variable, we now get probability distribution. Because we cannot describe, because we want to understand the behavior of random variables, that led to what we call the probability distribution. And in our probability distribution, we explain what a probability function is. And under that, we say that there are two different types of probability distribution. We say the discrete probability distribution. And by discrete, we means that when we are looking for a random variable that is finite or countable, we say that they are discrete. We're looking for an event that is countable or is finite, we say that we are considering discrete probability distribution. We also say that once when we are looking for an event that is a random variable, that is we want to understand the behavior of a random variable, that the occurrence is not finite, then we say that that's a continuous probability distribution function. We also talk about the probability function and the cumulative distribution function. We talked about the mean, which is the expectation, and we understand what the mean is. And then we also talk about the variance. We know that the mean is one of the tools that we tend to understand the measure, to be measure of position or central tendency. And then the variance helps us to measure the measure of dispersion, or how spread the event, uh, the occurrence of the events is. And today we will be talking about the moment generating functions, their properties and uses. Now, under these moment generating functions, we may not actually fully understand, maybe see clearly their maybe practical application now. But as we go deep, we will see that it helps us to be able to characterize these probability distribution functions. So when we start dealing with individual different probability uh, distribution, whether in the discrete or in the continuous case, we will see how the moment generating function helps us to generate some properties of these distributions. So we will look at what a moment generating function is, its properties, and what it is used for. All right. So what is the moment generating function definition now? Now, the moment generating function, otherwise tag MGF, as we can see there, is a function often used to characterize the distribution of a random variable. So, just like I explained earlier on, I say that the moment generating function is a function that helps us to be able to get some characteristics of the distribution of a random variable. So, we will see how we can get the moment generating function of a discrete random variable distribution, and then also the method of getting the moment generating function of a continuous distribution function. So the moment generating function, otherwise called the MGF, of a random variable x is a function given by mx of t, as we can see here. mx of t, and it is defined by this uh, quantity here in equation 1. So the quantity in equation 1, here we can see m subscript x of t equal to, so this t here is the event, this t here yeah, equal to, is the function equal to the expectation of the e to the power of t of x, close bracket, comma, where t belongs to this quantity here, to t here, capital letter T here. So t here, small t here is a subset of capital letter T, or small t here belongs, is in the interval. This t here is an interval or a range of value. So this small t here is a value that is contained in this range of value. So provided expectation is finite, or provided that the expectation exists. Now this might look somehow abstract, especially for some of us who have not dealt with this moment generating function before. But for some of us who are mathematically inclined, uh, by just looking at this, we can clearly understood or see how it plays out. But nevertheless, that does not stop us from learning it. And as we go on, we will understand more and more uh, how this mathematical quantity works out. So what are the properties of a moment generating function? Now from equation 1 that we have here, from equation 1 here, we can see here, uh, we see that the moment generating function is always positive. Yes, it is exponential quantity here that we have.
Sorry, your voice is fluctuating. I don't know if it's the network. We can't hear
Okay,
you in between at times. So, and at this time, it's so crucial we understand everything.
okay, all right. How about now?
Yeah, it's clear, but all of a sudden, it faints away. So that's one thing that,
Okay, I'll work on it. I'll work
yeah.
on it.
Thank you.
So, yeah, you're welcome. So we see that the moment generating function is always positive. So it will always be positive from our definition in one above. And then also, it is clear that 0 also belongs to t. 0 also belongs to that range of value t. And because of that, uh, that range of value t is what we also call domain. So it is a domain, or like the sample space, like what we explaining earlier on. So that t there is the domain. And from the domain, we can tell that 0 is uh, also belongs to that domain T. And the moment generating function of 1. So let's just store that at the back of our mind. Now 3, if the quantity small letter t here is greater than 0 and is in T, then 0 and T are proper subsets of the domain capital letter T here. I come again. If T is greater than 0 as is in T, then the domain, these are interval 0, comma T, is a proper subset of the domain capital letter T.
Hello, Jacob. Good evening.
Yeah, even Alima, you're welcome.
Thank you. Are you sharing your screen? Because I can't see anything.
You can see?
Yes.
I don't know. Mrs. Ebun, can you see my screen?
And I believe others can see as well.
Okay, but you can see.
Yes, I can see.
You presenting a slide?
Yeah.
Yes,
I can.
you can see. Maybe you should log in, log out and log in again.
Uh-huh.
All right, sorry about that. Can we continue? So similarly, if t here, small letter t here is less than 0 and it is in T, then the range of values, this interval 0, t, this closed interval 0, t, is a proper subset of the domain capital letter T. This shows that the domain of definition of a moment generating function is always an interval. It is always an interval. Now, this interval could be degenerate, that is, t is equal to 0, finite, that is countable, or it can be infinite, that is uncountable. But in general, there's no implication on the openness or closeness at the endpoints. So there's no implication whether it is open at the endpoint or is closed at the endpoint. It does not imply anything. So a simple example where the moment generating function is defined only at t equals 0 is the Cauchy distribution. So we're going to look at the Cauchy distribution. It's one of the distributions that we're going to look at. That if we have time, we can look at the Cauchy distribution. But just know that the Cauchy, the moment generating function at t equals 0 is a special case of the Cauchy distribution. All right. In the discrete case, so let's take a look at.
Sorry, I raised up my hand, but you didn't get to see it.
Oh, okay, all right.
The slide before this one, please.
Okay, all right. This one?
Yeah, the number 4.
Yes.
I tend to be a bit confused because if t is less than 0, then are we
Yes.
not meant to write the interval as t, 0, just for clarity, rather than 0, t, because t is less than 0. I'm just asking so that we
Okay.
can, do you understand what I'm saying there?
I understand what you're saying.
Yeah.
But it does not matter, Sha, but you can write it that way too.
Because t tends to be negative and less than 0.
Yeah,
Okay.
I think I agree. I agree.
That's why I made a statement down here. Can you see it? I say, but in general, there is no implication on the openness or closeness at the endpoints.
Okay. But it makes it more clearer as t, 0.
Okay. Yeah, I understand.
Yeah.
But for moment generating function,
yeah,
there's no implication whether it is closed or open at the endpoint. So
okay.
whether it is closed or open, there's no implication. It does not imply anything.
Yeah, yes. Thank you. Yeah.
All right. Now, let's take note of this, very important, because anywhere we see this, something like this, we should be able to understand what it's talking about. So in the discrete case, the moment generating function is equal to this quantity here. Can we see the quantity P subscript X times, here P subscript S times E of T of X. So anywhere we see this, we are trying to find the moment generating function of a discrete probability distribution. We're trying to characterize some functions of the discrete probability. And then anywhere we see integral over the range, this range here is dependent on the range of the distribution. But the range is from negative infinity to positive infinity here. So anywhere we see an integral from negative infinity to positive infinity of the range of a distribution like this, then it is continuous. Here, we're integrating, we're putting this quantity here, E of T of X, we're multiplying it by the cumulative distribution function. We have explained what a cumulative distribution function is in our last class. So here, this small f of x is the cumulative distribution function, then d of x.
Hello.
Yes.
I raised my hand. Can we go to the previous slide? Okay, yeah, here.
Yes.
Sorry, I always like some narratives around the symbols, unless I'm being told that I should just take those symbols and commit it to memory and just move on like that.
All right.
When I'm saying that in the discrete case, mx is equal to P of x. What is P of x? Is it probability function, or I should just take that P of x as P of x?
Yeah, it's probability function, but it's just like it's just like a symbol to tell us that what we're actually doing there, we're summing. In the discrete case of a probability distribution, you're actually summing.
Yes.
Yes, because it is discrete, it's countable.
Okay.
But in the continuous case, you don't sum, you take the you integrate.
Okay. So
Yeah. So
maybe in case of another time, maybe that additional narratives or explanation around it will also
uh,
help to drive it home.
no,
Please.
all right. No, no, no. We have already explained those things now. Before now, we've already explained the probability function of a discrete random variable, the cumulative distribution function of a discrete random variable in the previous class. I don't know whether you are in the last class.
No,
Well, I
what
was in
Stoinde is trying to say is that rather than we calling it P of X, we should kind of say it in a way that it can stick to the brain by saying the probability distribution of discrete, that so that we can, I
exactly.
understand you've explained, but once you say P of X, it's like it's going to disappear in the next moment. So I
Oh, okay,
understand where it's
I
coming from.
understand. But I wrote it here. I don't know whether it's not. I say in the discrete case, m of x, mx here, like I explained, I will say is moment generating for is equal to this quantity here
Yes, and
in the
that P of
discrete case.
X is
Is
it related to, yeah.
is in the you are trying to find the moment generating function of the discrete case. So you is related to this quantity here.
Okay.
Do you understand? When we start, that's why I say this one is a bit it looks more a bit abstract, more
Okay.
mathematical.
Okay.
You understand? But when we start looking for the moment generating functions of different distributions, we are going
Yeah.
to look for them.
Okay. All right.
So here we're just trying to introduce the moment generating function.
The
Remember, like I
formula.
said earlier on, yeah, I said that. Let me go back. I said that the moment generating function is a function that is often used. It helps us to characterize the distribution of a random variable.
Okay.
Do you
Okay.
understand?
Yeah.
Yeah, so the moment generating function. So now we use the moment generating function to generate the first moment, the second moment, and so on and so forth. That's what we call the first moment, second moment, and so on and so forth of a distribution. Do you get?
Yeah.
Yeah. So this is just like an introduction to tell us that there is something called the moment generating function, mg of x, which is the expectation of et of x as it is here. So we use it to characterize the distribution of a random variable. If it is in the discrete case, we say it looks like this quantity here.
Okay. The
This
way it's coming to my head now, the other
uh,
slide before this one, it's like the moment generating function is the no the one before this one.
okay,
Yeah, the moment generating function of an event is it t is the expected value of each moment. Like you said, we have the first moment, the second moment. So the t will stand for each moment, isn't it?
which of the t?
T, the one in brackets.
Okay, no, this et of x, are you seeing it?
Yeah.
If you notice, you see that it's a quantity that will be multiplied once you are taking. Do you understand what I'm saying? That
Yeah,
will be
but that
multiplied.
T yeah, is the T,
So if
that
you look
small
at
T. Where is it
eh,
coming from?
so
Is
if
it
you look at this this small t is the event.
aha, that's what I said. So the expected event each each time, the first one, the first moment, what happened, the expected, the second one. So when T is 0, T is 1, or T could be minus 1 or minus 2 each. So we have a value for each event of T, where
Yeah, yeah,
E is the
exactly.
expected value.
Exactly. I understand where you're having some
I'm
some
I'm trying not to cram it like coin they said.
okay. All right, okay. This is what we should
Exactly. Because I think it's very, very important that
Yeah.
it makes it easier for one to digest and, remember
yeah,
if there is
yeah.
direct understanding. Right. So
I
that is why
understand.
we have this
Mm,
discussion.
I understand. But
okay.
for now, ba,
Yeah.
instead of us to suffer our brains trying to cram it, or let us
Okay.
understand that there's a
Continue.
quantity
Okay.
that looks
All
like
right.
this.
All right. Okay.
Yes, so we use it
Thank
for
you.
moment generating function.
All
Is
right.
that okay? Is that clear enough?
Yes, it is. The formula is clear and well known. We just
Yeah.
want to create a narrative around it.
Okay. All right. It's cool. It's cool. I like the questions. It shows that we're actually interested in what is there, not
Yes.
just
Yeah. In
not
knowing
just
it. Yeah,
cramming.
that's it. We want to know.
Yeah, that's
Thank
nice.
you. All right.
Yeah. So a time will come, we'll start calculating moment, we'll start generating functions of some distribution. So when we start doing that, this all these things will be clearer. Is that okay?
Yeah, yeah. Thank you very much. Thank you.
But we should know that if it is in the discrete case, this is what we'll actually be doing. When we start doing them at putting values, we understand more. While if it is in the continuous case, this is what we are going to do. This will integrate over this range of intervals. Yeah. The x, of course, the x. You know, if you are integrating, you have the x. Now, uses of the moment generating function. The moment generating function has great practical relevance. Yes, it has great practical relevance, and this is the reason. It has great practical relevance because one, it can be used to easily derive moments. So you see, like I was explaining earlier on, we use it to derive moments. Then also, its derivative at zero are equal to the moments of the random variable. Now, secondly, we use the moment generating function as a probability. We say we use it to determine the probability distribution uniquely. So a probability distribution is uniquely determined by its moment generating function. So if we want to, uh, well, maybe when we start doing them, giving examples, we understand what we mean by these things. But we use it to uniquely determine, we use moment generating function to uniquely determine the probability distribution of a random variable. Then, thirdly, uh, the fact in two here, coupled with the analytical tractability of moment generating functions, makes them a handy tool for solving several problems. Such problems could include deriving the distribution of a sum of two or more random variables. So we'll see that when we start dealing with some examples. But we are not doing any examples under moment generating function today. We are only trying to introduce its properties, and then what it is used for. So as time goes on, and as we start dealing with each individual probability, and we start deriving some moments using the moment generating function, we'll see how important it is and how it's being used. Now, discrete probability distributions. So we're going to talk about discrete probability distribution. Remember, we see that a discrete probability distribution is distributions that are countable or finite. And don't forget, we say that probability distribution actually describes the behavior of a random variable, how that random variable behaves. And don't forget, we say that random variable is an event. For instance, let me just give an instance so that we will have a clearer picture. For instance, if you are were interested in taking some information from those people who queue in the ATM, for instance, the time it takes for one to be served in the ATM or served in the uh, E3, then we see that it takes some time. It deals with time, and then after the person, the first person in front, after within the next person, that is what we. It's a continuous distribution, but that is an example sorry, it's a discrete distribution, but that's an example of what we call the Poisson distribution. The Poisson, some people say Poisson. So when we start looking at when we go deeper, because the Poisson is part of the discrete distribution that we're going to talk about this week or next week. So we'll see how we can characterize that. I believe maybe that is my explanation is a bit clearer. So that is how we got what we call the discrete probability distribution. It's countable. All right. Now remember, we define a random variable x. We said that if it's said to be discrete, if its range consists of a finite or countable number of values. If its range consists of a finite or countable number of values. I believe we know what finite is, or what we call countable. We can count them. And don't forget, in our previous classes, I say that usually we look at a discrete probability distribution as just integers. That is, they don't have, that's practically when we're doing calculations, we just look at them as observations that don't have decimal points. I don't know whether we remember when I said that in some classes before. I say practically we look at a discrete random variable as maybe a integers that they don't have decimal points. Then we look at continuous one just in a layman understanding as observations that have points like 5.26 something or 5 point. Maybe you are taking an observation, you are taking readings, and the random variable you are getting is in the form 5 point or 2 point or 0 point something something, then it is continuous because of the point something something something. It is not countable. But if it is they are integers, practically that is how we look at a discrete random variable. I believe that is clear. So discrete distribution is a probability distribution where the random variable can only take on a finite or countable number of values. Can only take on a finite or countable number of values is what we call the discrete distribution. Now, a discrete distribution is a
Please, I
probability.
want to quickly ask.
All right,
Can okay, you're almost there. Can it take a negative value? No.
that's a discrete.
Yeah.
You can take now, insofar as it is countable. Now you can count back negatively now,
Okay.
insofar as it is not
Decimal.
uh,
But
decimal.
it can be -1, -2, down, down, down.
Exactly, is
Okay.
discrete.
That's what I want to clear. All right. Thank
That's
you.
discrete.
Yeah.
Is that okay?
Yes.
So,
Thank you very much.
a discrete distribution is a probability distribution that depicts the occurrence of discrete or individually countable outcomes, such as one or two or yes or no. So let's say you are collecting data or you're observing the behavior of a particular event, and the information you are getting or the result you'll be getting is yes or no. For instance, uh, are you a Nigerian? Yes or no? Yes or no? These are discrete. They are discrete distributions, or true or false question. They are discrete because they are countable. So the binomial distribution, for instance, is a discrete, the binomial. So let's look at it. You see, one of the most popular experiments in statistics or in probability is that of flipping a coin, right? I'm sure we know that that's one of the most popular experiment in probability theory, flipping a coin, and then the other one is that of rolling a fair die.
Fair dice. Yeah.
Yes. So these are two of the most popular experiments in probability. So, and that of uh, um, flipping a coin is a binomial distribution because it either turns up a head or a tail. Now, if the experiment is done once, maybe before we go deep, let me just give this tidbit. If the experiment is done once, then it is a Bernoulli distribution. But if it is done n number of times, that's more than once. That's if we say a coin is flipped 3 times, then we have now entered binomial distribution. But if it is only flipped once, then it is a Bernoulli distribution. So don't worry. Just have this at the back of your mind. When we continue, we'll have more and more information on what we're trying to talk about, and we'll be able to understand the distribution or the behavior of an event that makes us to characterize it as a binomial distribution. So the binomial distribution, for example, is a discrete distribution that evaluates the probability of a yes or a no. Taking that example of a coin, a head or a tail outcome occurring over a given number of trials. So given the event's probability in each trial, such as flipping a coin 100 times and having the outcome be heads. So in this case, because the number of times the n there, remember I said that makes it a binomial distribution. Now, some key attributes of discrete probability distributions. Don't worry, we are going to give some examples of the most commonly used discrete probability distributions, and then we will be able to start using them to do some modeling to calculate some probability distribution, and then and so on and so forth. Uh, Remember the last time Elias was saying, the one that takes us in the risk assessment. He said when we start doing pricing and valuation pricing, when we start pricing, we will see how these different distributions are being calculated, how we use them. So some key attributes of discrete probability distributions. One, a discrete probability distribution counts occurrences that have countable or finite outcomes. So let us not forget, it counts occurrences that have countable or finite outcomes. Two, these distributions often involve statistical analysis of counts or how many times an event occurs. Another attribute of discrete probability distribution is in finance, discrete distributions are used in options pricing and forecasting market stocks or recession. So when we start the class of pricing and forecasting, we're able to see how we use discrete distributions to forecast and to also get options of pricing and recessions. Now some examples of discrete probability distribution. So let's look at some examples. Now some commonly used, because there are plenty, they are as much. In fact, day in day out, researchers are bringing in they are getting they are generating new distributions day in day out. So these old probability, the old distributions that we know, discrete distributions, they are there because we have been dealing with them. But if you start looking at some papers, you will see that if you go deep and deep into the probability theory and distribution, you see that there are people whose research is on generating new probability distributions. Some can be discrete, some can be continuous, and once they generate these distributions, they can now get their individual properties, statistical and mathematical properties, and then use them in some uh, 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 data and see how they do. And sometimes you see that they perform, some new distributions perform better than some other old distributions. But for this particular class, and to our scope, the scope of this class is not up to that one that we start learning other new distributions, but it's just for us to understand how it works and how we can apply it in actual in insurance or in actual science. So some most commonly used discrete distribution includes the binomial distribution that we have explained above, the Poisson distribution, or some people say Poisson distribution, uh, that requires a time to event. Then we have the Bernoulli distribution. I say it is a special case of the binomial distribution because the Bernoulli distributions, once you toss a coin and you just do it once, then you get the Bernoulli distribution. Then we also have what we call a discrete uniform distribution, the geometric distribution, the negative binomial distribution, etc. We also have the hypergeometric distribution, so on and so forth, and so on and so forth. So we will see how we can, maybe if time permits, we can venture into all these probability distributions separately. We'll see how they are being applied and their application, some attributes, and so on and so forth. If possible, we can even see how we can generate some of their characterization, maybe using the moment generating function, and so on and so forth, to get the first moment, second moment, and so on and so forth. And we'll see how they are being used. All right, so let's start with the binomial distribution. The binomial distribution. So an example of the binomial distribution is the experiment of tossing a coin. For example, if we toss a coin 3 times and we are interested in finding the probability of observing exactly 2 heads. So let's say we can say a coin is tossed 3 times. What is the probability that exactly two heads show off? So you see, that's an example of a binomial distribution. Remember, don't forget another important ingredient is the number of times here, which is the n, and then and so on and let us not also forget, because in this case of binomial distribution, we either have a success or a failure, because it is either head or tail, for instance, yes or no. So let's say we say that yes is our success, then automatically no is failure. Or if we say no is our success, then automatically yes is our failure. And what we do is that, in as much as we already have maybe yes, then for us to get the no, we can just say 1 minus the one that we already have, which gives us the other one. Remember, we see that the total probability is usually 1. The total probability is always 1. Now, the binomial distribution is useful for modeling problems in which you need to find probabilities for the number of successes in a series of independent trials. For instance, how many times will you toss a head? Or how many times will you hit a target? Or how many times will you guess the right answer on a test? And so on and so forth. And it is either you guess the answer right or wrong. It is either you hit the target or not. It's either you toss a head or tail. And if we do it a number of times, that's binomial distribution. In summary, if we are interested in getting successes of counts, and we know it's usually count, and we are taking the experiment an n number of times, then we're talking about a binomial distribution. Now, a proper definition now. An experiment is called a binomial distribution if all of the following hold. So this is a more proper definition, or let's say mathematical definition. An experiment is called a binomial experiment if all the following hold. One, if the experiment consists of n identical trials. For instance, tossing a coin is identical. We are tossing the coin maybe once, twice, 3 times, 4 times, continually n times. That's one characteristic of a binomial experiment. Two, if each trial has exactly two outcomes, success or a failure, usually referred to as success or a failure, and I've explained that. I said that yes or no, or you hit the target or not hit the target. You get the answer or don't get the answer. You guess it right or you guess it wrong. So two outcomes. That's the second characteristics of a binomial experiment. Either a success or a failure. Three, the third uh, characteristic is that the probability of success on each individual trial is always the same number. So P. For instance, don't know whether we understand. If we toast the first time, the probability of success should always be the same with when we toast the second time, with when we toast the third time, and with when we toast the nth time. Also, the probability of failure is then always 1 minus P, or we usually say Q. So P is success, Q is failure, but Q is 1 minus P. Probability of success here is equal to P. Probability of failure, 1 minus P. This is because the total probability is 1. And if we only have two options or two outcomes, then it means that if we get the first outcome, then when we subtract it from 1, we will get the other outcome. I don't know whether that is clear. I believe that's clear. So here we have P, probability of success equal to P, probability of failure 1 minus P. Then probability of failure, that's Q. It is also Q. So either 1 minus P or Q. So we have 1 minus P. Then finally, the trials are independent. The trials are independent. So all these four characteristics characterize a binomial experiment. So I believe that anywhere we see a binomial outcome, whether in any example, whether it is in insurance, in business, whether it's tossing of a coin, then we know that once we just hear the way the behavior of that kind of experiment or the behavior of that kind of scenario situation, we know that the outcome that we're expecting is a binomial distribution. All right, I believe that's clear. All right, Mrs. Ebun, please go ahead.
You just kind of get me to where I wanted to ask a question. Can
Okay.
we look for one example in the insurance world where the binomial distribution is taken? Because something is coming to my brain that I know when you're trying to get data for your client, and you talk about for what's it called? Is it that male or female? So
Yes.
can we say the gender distribution will be binomial? I'm trying to look for something to hold on to and create that thing in a way that one can easily look, for example, with the daily occurrence around us.
Okay. Yeah, it depends on how you want to collect the data. For instance, if you consider the male or female as success or
Mhm.
failure, then it is
Yeah,
binomial. But if you're just taking the data just like that, you just want to know, you understand, but it may not be binomial. But if you consider that, okay, if we want to select the person that will maybe get the job, what is the
yeah.
probability that is a male?
Mm.
Then it is binomial.
Knowing for sure that it's just two outcomes, is that male or female,
Exactly, either
then it's
male or
going to be
female.
binomial distribution.
Exactly. But you must do it a number of times.
Yeah, n must be greater than one.
Exactly. So if n is equal to one, then it is Bernoulli.
A
That's
binomial, yes.
all right. All right. That's
Okay.
clear, right?
Yes. So
Okay.
another example again
Yeah,
in
there's an example
insurance
down.
world.
There's an example here. See the example here. We're going to solve it.
Okay, thank you.
See it here.
Okay.
Yeah. There are some other examples too down. See one here. I see it.
Yes, thank you very much. That's what I'm saying. Yeah.
All right. All right.
Thank you.
Okay. I think we're here, right? All
So
right. So we have described a binomial experiment. So now let's describe a binomial distribution. So we are going to get the 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 p of, how do I even put it? The probability function. Sorry, we are trying to get the probability function. Remember this quantity in one of our class. Can we remember this quantity?
yes, yes,
Yes, something
yes.
like this. We say p of s equal to a particular whether k this thing. So once we see p of s equal to this it is discrete. And then for a binomial distribution, actually there are some little examples that I skip uh, because it is expected that it should not be part of the class, because if we start doing it, it will actually take us far away from what we actually need for this particular class. For
Okay.
instance, we can have a tree diagram that characterize head or tail.
Hmm.
Then it will lead us to what we call permutation and combination.
Hmm. Okay.
And then that is what will lead us to this particular probability function of a binomial that we have here. Yes, but
Hmm.
because that is not needed or is needed, it's important, but it's expected that we have known it. So that's why I didn't introduce it here. But let's understand that this is how we got this probability function here for the
Okay.
binomial n combination k, p raised to the power of k times 1 minus p raised to the power of n minus k. Actually, what it means is that if you the first experiment you are taking the permutation n combination k, you see n. Let's say you are taking the experiment 100 times, your n
Hmm.
will now be 100. Combination k,
Okay.
maybe
Well,
the first one maybe that's the first one 1. Then this probability of success here p raised to the power of 1
it's the first one.
times, yes, times q, which we don't forget. Let's also forget 1 minus p
Yeah.
raised to the power of n minus k. So when we take the second one again, that's how we continue doing. We'll continue doing. When we come to p of x equal to 2, we do the same thing again. These things continue changing
Yeah.
and so on and so forth. So here we see that they say for k equals 0, 1, continually to n. I believe that's clear.
So for k equal to 0, it shows that
Yes.
we're not looking for
It
because
shows that
it's
it shows that you don't even take the experiment.
okay.
That's k equals 0 now.
Okay. Okay.
Yes. But it's a possibility, Sha. That's why we say for k equals to 0, 1. But if you do for k equals to 0, you know that
And
here
that will
we now
be
have,
automatically looking after the failure part. That's what I'm looking at.
I think everything will even be one self, something like that. I don't know, Sha. But
Thinking
yes,
that if we look at this,
mm,
the N there is the number of trials,
Yeah.
yes,
and I think the X here is like the number
the X,
of the
there's
random
no X.
variable for like maybe a particular event. So if
Yes, mm-hmm,
X is equal, if K is 0,
mm-hmm,
perhaps I'm saying that my success in N
trials
trials
Zero.
is 0.
is 0. Yeah, thank you
That's
Yeah,
very much.
that is
Thank you.
what I'm saying. It
Exactly.
shows that
Yes, that is what it
it's failure. Yeah.
exactly. Yes, exactly. That's how it is. That's exactly how it is. Thank you.
Yeah.
All right. So example one. Let's look at example one now. So that all the mathematical lessons that we've been putting on top, let's do some practice, some examples, so that we'll see how we're actually talking about.
Hmm.
So example one here, even though I put 5.4 here, but it's example one.
Yeah.
Let's just So let x be the number of heads in three tosses. So we see now, even
And
without them telling us that it's binomial, we know that there's toss of a coin, of a fair coin, and then there is n, three tosses. And then we say let x be the number of heads. We're interested in the success, that's head. And we have three tosses n. And we know that it is either head or tail. So that makes it binomial automatically.
hmm.
So questions like this, they don't need to tell us that binomial. For instance, maybe they say question one or exercise one. They can't put binomial for you in front.
Yeah.
And from reading the question alone, you know that it is binomial. Once you get some characteristics, for instance, you know that you are expecting success or failure, and you know that you are doing it a number of times. All right, so here n is equal to, and okay, let us not forget this fair coin.
Okay.
Sorry, my system battery is getting low. Sorry, I'm coming. Let's not forget this fair coin. Remember, we say it must be identical. The experiment must be in one of the characteristics that we explained earlier on. We say it must be the same. The first experiment must be the same experiment with the second experiment, and so on and so forth. So here we have that n equals to 3, and then probability of success is 1 all over 2, right? Because it is either one head shows up in the sample space, head or tail. So the probability is 1 over 2 or 0.5. So using equation 5.1 that we have here, equation 5.1, this equation here, we're using this equation to solve it. So using this equation, we have that we are looking um, uh, for k equals to, we can replicate the value of p of x equals to 2. So here we have p of x equal to 2. And then using that equation 5.1, we have 3 combination 2, 1 all over 2 raised to the power of 2 times 1 all over 2 raised to the power of 1. That's 3 minus, remember, n minus k here. So 3 minus 2, we have 1, equal to 3 multiplied by 1 over 8. So this gives us 3 over 8. Now let's note that the term 3 over 2 gives the number of branches with exactly 2 heads. That's the combination, like I explained, 3 combination 2. And the term 1 over 2 raised to the power of 2 multiplied by 1 over 2 raised to the power of 1 gives the probability of single branch with 2 heads. 1 over 2 for success, 1 over 2 for failure. If we only have for success, to get for failure, we say 1 minus 1 over 2, which is equal to 1 over 2 half, or 1 minus 0.5, which is equal to 0.5, which is equal to 1 over 2. So these are our answer. Now,
Sorry, if you
explanation.
go back to that equation,
Yes.
so in literal, in me telling a layman, so one can say that the probability distribution of x in the
Of getting
second
two heads,
of
of
okay,
getting two heads in three tosses is equal to 3 over 8.
Okay, because X is the number of heads. So
Yes.
of getting two, that's what I want to. So the probability of getting two, I can't see your board again, please.
Yeah.
Of
Sorry.
getting,
The
yeah.
I'm coming.
So, okay, because S is defined as the sources of getting two. Okay, okay, I got it now.
Sorry, just give me a while. My system just ran down, but
No
let me
problems.
find another alternative now. I will share the
Mm,
screen right away.
okay.
Just give me some time. Yes. All right. Can you see my screen? Can you see my screen now?
Yes.
Okay. The screen is visible now, right? All right. Can we see the solution where we stop? Yeah. Hello, ma.
Yes, yes, I can see that. So the probability of the number of heads equal to two in three trials or in
Tosses.
three
Yeah.
tosses.
Yes.
Okay.
Yes, it's
Yeah.
equal to 0/8. Now, when we want to calculate, let's say, insurance premium, or want to see the probability of insure, this is where the probability actually shows value. So that's when we know how much the person will be paying premium. So once we get the probability, we fix in all we need, because once we be able to get, then multiplying it by that amount of the what the insurer the what the insured will be paid.
Mm,
Yes. So when we multiply this probability by that amount, then we can now get the amount of the premium that he will be paying, let's say monthly, or I don't know where we understand what I'm talking about.
yeah, yes, yes,
Yes.
I do.
Yeah. So but now, our in this class, we're only interested in understanding the way the probability works out. Yes. So when we start the course pricing and valuation, I think Elias will take that one. I don't know, maybe it's this semester or next semester. We can now see how this works out with, maybe, let's say, getting insurance premium or valuation or pricing and so on and so forth.
Mm.
All right. So, but for this is the case for a binomial distribution. All right. So explanations to what we have. The the example should make clear the meaning of the terms in equation 5.1. For instance, that term p raised to the power of k times q raised to the power of n minus k gives the probability of a single branch with exactly k successes. Then the term n combination k gives the number of branches with exactly k successes. I believe that's clear.
Yeah.
So binomial distribution, mean and variance.
Mm,
So how can we get the mean and variance of a binomial distribution? Recall, we see that the mean is also called expectation.
mm,
Yes. So if x is a binomial random variable with n trials and probability of success is equal to small letter p,
mm,
then the expectation of x, or the mean of that event x, because it is random variable, is np. Now, there are some other small mathematical steps that we're taking to get this np,
mm,
but I don't think if we want to go into them, it will make the class more boring.
mm.
Yeah, that would be more appropriate for those who are actually studying the mathematical aspect more, like those in statistics. But since we are applying it, I feel that. But if we say it's okay, we can learn how we generated. We know that the expectation of a binomial random variable is NP. If we're interested, we can be doing them. But else, we can just know that the expectation of a random variable, if it is binomial, is NP, n multiplied by number of times multiplied by success, number of times the event, or number of the trials multiplied by the success, which is P, which is given in equation 5.2a, as we can see. Then the variance of a binomial random variable is NPQ, or n times p times q. That's the number of times multiplied by the probability of success multiplied by the probability of failure. So if you like, you can represent it as NPQ. If you like, you can represent it as NP times 1 minus P, where 1 minus P is Q, as we can see in equation 5.2b. I believe that's clear. So when we're looking for the expectation or the mean of a binomial experiment, we know that we're multiplying the number of times by the probability. So if we go back to this here, we can also actually find the mean here. This will be 3 times 1 over 2. We get the mean of this experiment. And for the variance, we have 3 times 1 over 2 times 1 over 2, and we get the variance. Now, properties of mean and variance of binomial distribution. Now, the properties of mean and variance of binomial distribution, since P and Q are numerically less than or equal to 1, let us not forget, since we only have two outcomes, success and failure, it means that it is either they are equal to 1 or they are less than 1. That's the total, because success plus failure is our total probability in a binomial trial or Bernoulli trial. And we know that total probability is always equal to 1. So if we are P and Q and it's numerically less than 1, then NPQ will always be less than NP. NPQ will always be less than NP. That's the variance will always be less than the mean. The variance will always be less than the mean. MPQ is variance. Don't forget, MPQ here is variance and MP is mean. So the mean variance will always be less than the mean. 1. The variance of a binomial random binomial variable is always less than its mean. 2. The variance of binomial variable x attains its maximum value at p is equal to q, which is equal to 0.5. That's at the middle, And this maximum value is n all over 4. N all over 4. 3. The variance of a distribution measures how spread out the data is. And then related is the standard deviation, which we already know it is the square root of the variance. The square root of the variance useful. Useful due to being in the same units as the data. Now 4. The mean or expected value of a distribution, remember we're talking about the binomial distribution, gives useful information about what average one would expect from a large number of repeated trials. So that's actually what the mean does. It gives us what is the average that we would expect from a large number of repeated trials. So when we repeat an experiment, a binomial experiment, a large number of times, the mean actually tells us, okay, what is the average that we can expect? Okay, if we do this, what are we expecting? If we take this, if we do this experiment this number of times, and that's what the mean tends to measure. It's a measure of central tendency. Now, example 2. Let x be the number of heads in 3 tosses of a fair coin. And we know that this is also binomial. Since x is binomial with n equals to 3 and p equals 0.5. Sorry, that's supposed to be equal to, not minus. And p equals 0.5, then this is the solution. 1.
Oh.
Are you raising your hands?
No. I said okay.
Okay. Yeah, sorry, that p there is supposed, that minus is supposed to be
Yeah, you
p
said supposed
equals.
to be equal to, and I said
Yes,
okay.
yes, yes. Yeah, it's supposed to be equal to. So if we take our time and do the multiplication, here we can have that the expectation or the mean, the e of x, that's the number 1, because I'm just solving directly. We see that the mean here is equal to 3 times 0.5. If we have not forgotten, the mean of a binomial distribution is NP, where n is the number of trials and p is the probability. So here our probability is 0.5 and our Number of trials is 3. So we have 3 times 0.5, which gives us 1.5. So the mean is 1.5. And then our variance is NPQ. So we have 3 times 0.5 times 0.5, or times 1 minus 0.5. So this gives us 0.75. So from here, we can see one of the characteristics of the mean and variance of a binomial distribution. We see that the variance is 0.5 and the mean is 1.5, which shows that the variance is less than the mean. So if you are doing any calculation of binomial distribution, maybe you're looking for mean and variance, and your variance is greater than the mean, then you are wrong. So the variance must always be less than the mean in any binomial experiment. All right, application. So let's look at this application. This application to insurance. Now, example 5.9, insurance. Example 3, sorry. The 1979 to 81 United States life table given in Boas et al. So this is the paper that if you want to see this life table, the US, if you want to see the US life table of 1971 to 1981, let's consult the paper Boas et al. Boas et al. We will see the table. It gives the probability of death within 1 year for a 57-year-old person as 0.01059. So in that's the result of that particular table if we consult Boas et al. Now in actuarial notation, we use Q. Remember, death is the failure while being alive is a success. So we have Q of 57. This Q of 57 means the death of a 57-year-old. As we can see here, Q of 57 in this bracket, we see Q57. It means the death of a 57-year-old or the failure, because we are defining death as failure. We see that the probability is equal to 0.01059. Now, this is the question. Suppose that you are an insurance agent with 10 clients. So here, our 10 is now our what? N, right? With 10 clients,
Yeah.
yes, with 10 clients who have just reached age 57. So now these are we are just looking with our characteristics here is 57-year-old people. Sure. But it was known that the probability of any 57-year-old person to die is 0.01059. So you are willing to assume, remember we say suppose that you are the insurance agent and you have 10 clients, and these 10 clients they have reached 57 years, and you are willing to assume you are willing to assume that the deaths of the clients are independent events. We understand what we mean by independent events as we have explained in
Yes.
yes. So we assume that all of them they are independent events. What is the probability that all 10 survive the next year? That's our first question. We want to know, okay, what is the probability that all of 10 of them will not die in the next year? What is the probability that they will survive? What is the probability of success? In other words, if we consider surviving to be success and death to be failure. So what is the probability of success of the 10 of them in the next year? Then B, what is the probability that 9 will survive and exactly 1 will die during the next year? That 9 will survive and exactly 1 will die during the next year. All right, so with this piece of information, let's see how we can do the calculation. But I feel tempted to give us this one like assignment so that we're going to look at it more. But already have there are answers. There are answers here already. But we can go and put the formula that we have in 5.1. Remember? And then we'll see how we can do them. It's important that we try to solve them, not just look at it with our eyes like this. Maybe when we in our study time, we just take a pen and paper and write these things down and write them down because it will stick in the brain better. We understand what we're actually doing and what we're calculating more. Though there are softwares that calculate these things, but it's good to this actual mathematics. We are trying to understand the mathematics behind it. Yes. So what is the we say A, what is the probability that all 10 will survive the next year? And then B, we want to know or you want to know as the insurance agent, what is the probability that 9 will survive and exactly 1 will die the next year? All right, so solution. Now, if clients' debt are independent, because we have assumed that the debts are independent. If they are not independent, it will take a different turn because the combination now will now be changing the and so on and so forth. But we have already assumed that they are independent. So if the client's debts are independent, the number of survivors x, which is now our random variable, will be a binomial random variable with parameters n equals 10 and probability of success now will be 1 minus q. Remember, we gave q now. We say q, which we say that the probability of death, which is failure, q of 57 is equal to 0.01059. So that gives the probability of death of 57-year-olds. So if we come back here, we are now looking for our success. Our success will now be 1 minus q. Like I said earlier on, if you are giving success to get your failure, your q will also be 1 minus p. So if we do that, we will now get our probability of success to be equal to 0.98941 to 5 decimal places, 0.98941. So A, the probability that all 10 will survive the next year is 10 combination 10. Remember about all 10 survive. That's probability of S, the random variable X is equal to 10. So this gives us 10 combination 10 multiplied by probability of in this case now we don't have probability of failure because it is raised to the power of 0, which is equal to 1. That's 10 minus 10. Remember from the formula, 10 minus 10, that will give us 0. And then anything raised to the power of 0 is 1. So it does not have to reflect here. So that's why we did not reflect it here. That's why we only have the probability of success raised to the power of 10. And if you use your calculator, you get the approximate value of the probability of all 10 of them surviving the next year to be equal to 0.8990. And so, which means that there is a 0.89% or 0.89 probability of survival. Or if we want to turn it to percentage, which means that there is an 89% probability that 57-year-old will die. These 10 people that have been sampled, they will not die in the next year. There is an 89% or a 0.89901 probability approximately that they will not die in the next year. So we see that the probability that they will not die is actually a bit high. Now, if we want to look at also the probability that 9 will survive and exactly only 1 will die during the next year, then we have probability of x is equal to 9. Then we have our 10 combination 9 multiplied by 0.98941, which is probability of success raised to the power of 9, because we say 9, so we have n minus and so on and so forth, and then 0, we have k, and then 0.01059 raised to the power of n minus k, which is 1. That's 10 minus 1, which is 1. And if we do our calculation, we'll see that we have 0.09622. So which means there's approximately 9% chance that 9 of them will survive and only 1 will die in the next year. Or there's a probability of 0. We can actually change this probability 0.09622 to a percentage if we multiply by 100. And if we do that, we get 9.622%. So there's a 9.62% that only 1 of them will die in the next year, and that 9 of them will survive. I believe that is understandable. If there's any question, let's concerning these examples that I've done, please go on. Are we all there?
Yeah, fine.
Okay, there's no question, right?
Yeah, we're here.
Yes.
Okay, I believe it's very clear.
Mm. Yes to
Yes.
me. And I believe, yeah, yes to me.
Okay.
Yes to me also. At least so far so good.
Yeah.
All right. All right. So glad to know. All right. Cool. All right. So now summary. Now summary. So in summary, we did the recap of our last lesson, and we understood some things, and then we understood what a random variable is. We say it's a random event because it's random, then it's random variable. And then we also talk about probability distribution. We say that it describes the behavior of a random variable. Then we also explain, we say that if it is discrete, then we are looking at a finite number of events
Mm,
or countable. We say that if it is continuous, then it is infinite, or like I say, in practical terms, we are just considering,
continuous.
yes, integer, and then the other, if it is continuous, then it has decimals.
Yes. Mm.
Yeah. Then we also talked about the moment generating function. We say that it is important because it helps us to generate some properties of some random variables. So we say if we are getting the moment generating function of a discrete distribution, we say we use p subscript x e of t of raised to the power of t of x. And then we say if it is continuous, we take the integral over the intervals of that particular distribution from negative infinity to positive infinity. Generally, in general, we multiply it by et of x, and then we multiply by the probability function, and then the x. We integrate it over the interval. Then we also explain discrete probability distributions. We talk about, we say that discrete probability distribution are probability of counts of finite random variables. Then we explain that there are more. We say that there are different types. In fact, there are plenty. We have the binomial, the discrete uniform distribution. Even though we also have the continuous uniform distribution, but we say we have the binomial, the discrete uniform distribution, the hypergeometric distribution, the geometric distribution, the Bernoulli distribution, the Poisson distribution, and so on and so forth. And we talked about the binomial distribution. We say that the binomial distribution is simply an experiment that we are interested in success or failure. And we also say that this success or failure must be done a number of times, n number of times, and that characterize it as a binomial distribution. We gave some attributes of binomial distribution. We explain the mean and variance of a binomial distribution. We see the mean is NP is equal to mean or expectation of the random variable. If it is binomial, the mean is equal to NP, that's number of trials multiplied by the probability. And then we'll also see that for the variance, it is NPQ. And we'll see that the mean actually tells us, in average, if we perform an experiment a number of times and it is binomial, we're interested in success or failure, it tells us an average, the average number of people or the average number of what we expect in that experiment. So we give examples and some practical example. We give the formula. Remember in formula 5, equation 5.1, the formula that we use to calculate some binomial distribution. We say n combination k multiplied by p raised to the power of n, open bracket, 1 minus p or q raised to the power of n minus k. Now we also give some example, and the last example that we gave on insurance. So we have explained. So far so good. I believe that we must have understood. If there are some other questions, there is time for question. We are going to ask them. Then finally, we have some exercises for the next class. Somebody say exercises. I know now when we say these exercises now, some people, someone will say, we have not finished the last exercises. We are still having some other exercises. Please, let's try and do the other exercises because we know they all form part of our continuous assessment. Very, very important. So let's try and do those other ones and submit, and also do this one. So we'll submit the
Are
other
we
exercises.
submitting this one as well?
Yes, ma. Every assignment should be submitted.
Okay, no, I just want to know because the first one I was trying to solve on paper. So I should do I mean try and submit it via the link. Okay.
Yes, yes.
Not a
I will
problem.
send. We will send it, sir.
That's not a problem.
Okay. All right. All right. We will. we will resend the link again.
Mm.
Then when we log in, we'll go and see all the assignments there. Then we'll just pick them and then solve them, and then we'll send the link for submission. You know that the assignments there, all the assignments and the materials are in a particular drive, right?
Mm.
Yeah.
Okay.
So we'll send a link for a Google form that you just go there, fill in your name, and then the course, and then you upload the assignments. Yeah. So
Okay,
that
thank you. This
yeah, that
one
would be
seems simpler compared to the first one. The first
all
one
right.
is so abstract.
All right.
Right.
Yeah, this
I,
one's
I
this
agree with you, Ebu.
Oh, you see,
okay.
I'm not the only one. You see what I'm saying?
Okay. All right. No wahala. No wahala. We'll see how it goes.
All right. Yeah, it is. We
So
are good students.
yeah, this one we have even given the answer in this one. So
Yes,
if you are not
already we see. So that's I said the first one was so abstract, but I
okay,
mean, we
there's no
give it.
answer. There's no answer in the first one, Abi.
Yeah.
All right, but we still need to show the working so that we
Yeah,
will
we will.
make
We
sure
will.
it corroborates with the answer that we have here.
Okay.
Yeah,
Thank you.
yeah. Then we have this is not the only exercise. There's another one, the second one. So
Okay.
this is the second one. Can I
Okay.
read them? Can I read them quickly, or let me just leave them?
Yeah, whichever way you want.
Okay, let me read them quickly. The first assignment says, suppose it is known that 5% of adults who take a certain medication experience negative side effects. Find the probability that more than a certain number of patients in a random sample of 100 will experience negative side effects.
Mm,
1. X greater than 5 patients will
mm.
experience side
Yes,
effects.
I said it's good.
Yeah,
Our
X
hen
greater
is
than 10.
100.
Yeah,
You
N
see
is
that?
and, and we know that looking at this experiment, we know that it is where our outcome is either success or failure.
Or
I don't know
failure,
whether
you see?
yes, because
And
because we want to know whether they will experience the negative effects or not.
okay.
You understand? But so that makes
Yeah.
it binomial
Yeah.
because they say they take a certain medication, they experience side effect. So if you experience side effect, then
That's success
that's success. Or
of
maybe if
this
we say failure,
experiment. Yes, of this
eh,
experiment.
then if you do not, then that's the other one.
Yeah.
Good. So this gives medical professionals an idea of how likely it is that more than a certain number of patients will experience the negative side effects.
Hmm.
Now, 2, an agent sells life insurance policies to 5 equally aged, healthy people. According to recent data, the probability of a person living in these conditions for 30 years or more is 2 over 3. Calculate the probability that after 30 years, case 1, all 5 people are living. Case 2, at least 3 people are living. And case 3, exactly 2 people are still living. I believe it's
See?
clear. Let's just take our time and look at
Okay,
them.
we'll
They'll be
try.
clear. Yes. All right. So we have come to okay. Now next class we'll look at other commonly used discrete distribution like the Poisson distribution, the Bernoulli distribution, the discrete uniform distribution, and the others, geometric distribution, and the others.
Okay.
That's we'll look at them in the next class, just like we look at the binomial distribution.
Okay.
Yes. So questions.
Okay, I think I have a couple of questions.
Couple, sir.
Okay, thank you very much.
Yeah, go ahead, sir. Yes.
Um, the assignment,
Yes.
are we allowed to write, do the attempted solution on uh, sheets of papers like not necessarily A4, but at least higher education sheets and submit, or are we expected to type it?
Okay, I understand. Now, since we are learning, I think it would have been very nice if we use, aware of the scientific typesetting, LaTeX, or some people say latex.
Latex, or is it
Uh,
latex?
I've
LaTeX,
not heard of it though. How do you spell it? Are we going to
LaTeX.
L
download it?
Latex.
L
Yes, yes.
A T E S. So you
I don't know.
download or what?
Yes, if you can download so that we will just translate the assignment there and submit, that would be great too.
Ha.
How do we see it?
I've not even heard of it
Okay.
before. Will you send the link or is this something you just Google?
You can go on YouTube and see how you can download the Mixtex and then the Text Studio.
Father in heaven.
Is
This
that-
is where the trouble is.
but it will be great if we do it there. But
Lates.
E
X,
Is
X
it S for sugar or saxophone?
zero
no, X for xylophone.
Xerox.
Yes, yeah,
Okay,
Xerox or something.
that is
So
Jesus.
if we can use that one, it will be great too. I don't know. That's
Ha.
what I used to actually type this presentation.
Thank you, Kende. Oh
But
my
Mhm.
God.
sorry. Additionally, are you there with me?
Yes.
Yes.
You can actually employ the use of the online LaTeX editor.
Okay. Okay.
In that case, you don't need to install a LaTeX compiler and the studio. I don't know whether we understand.
I
You
Okay.
can
don't
just
know.
Okay.
yes, you
Latest
can
what?
just
Hey.
LaTeX compiler the latest software.
Online artist editor.
So you can as well use the online LaTeX editor.
Online latest editor. Okay.
Yes, you
Editor.
to do that you go to Overleaf.
Hey.
The informations are much cool.
Hey. It's the going here and there, and then you get those online.
Okay, all right. This is what we're going to do so that we'll not end up giving too many information and at the end of the day we'll not do one.
Okay.
Just go
So,
and learn more. Just go and learn more about the LaTeX. Then when we come in our next class, we will give more directions on how you can go about it.
so
Is
if
that
I
okay?
don't get it, like when they said, I can write it and scan it to you or wherever.
No wahala. It's fine.
Okay.
You can chat me on WhatsApp too. I will.
No, it's even the typing of exponential, all those things that is trouble. So,
Mm, yeah.
lattice overleaf. So if I click on lattice overleaf, I would now say take me to online latest
No,
editor. That's
you click on Overleaf. It
overleaf, and
opens.
then
Yes, it opens. Then you will now create an account with Overleaf. Then you will look for a LaTeX template and just enter there. It will even show you how things are done there. Then you from there you can now be editing from their file.
it's
Once
just
you
that
finish
it's
editing,
good to know all these things now. An online
yeah,
editor. So I'll take it and say on overleaf online latest editor.
just type Overleaf.
Oh, I've seen one.
If you see Overleaf, then click on Overleaf. You will see
Yeah.
option to
I
create an
say
account.
get
You create an
started
account.
now. Register.
Eh,
How
no,
much will I be paying?
no. I think it's free except if you want to subscribe. But there's a way you use it free.
You see?
You they give. That's another information.
Hmm.
I don't know.
Ah,
Well,
if coin they finish using it, let me know. They are not going to charge you.
all right. So no wahala. No wahala.
I've because you say get started. Register using Google, email,
I will
register
do that.
using ORCID. Me as I am, don't want anybody to kill me. Oh. I want to be alive. Because it's easy for them to keep deducting things from your account and you will know.
Yeah, no. The only thing you don't enter any of your credit card details. No, you don't do that.
Okay.
You just keep there is free trial. You keep on using the free trial, except
Okay.
if you overuse the daily number of trials, then you have to leave it till the next day again before you can compile.
Oh,
That's just how it is.
okay. That's it.
Yes. Except maybe if you want to subscribe to unlimited, you understand that's when you pay. But that one is not needed. You can use it
Okay.
free and continue using it. Yes.
Okay. Thank you
So,
very
sir,
much.
any more questions?
Yeah, thank you. Except to us just make a plea that in the next class,
Yes, sir.
all those various distribution, it's
Yeah.
always very interesting and more enlightening if we can have um, use cases, a scenario, so that it makes it easier to drive home the point and
Okay.
the importance of those various distributions. Thank you.
Distributions. It's all right, sir. That will be taken care of.
So it's like binomial is useful in life insurance. Proper.
Yeah, most of it depends on the scenario, sha.
Okay.
But it's
Because
useful,
it's like
yes.
life and death. Death, which is free
Okay.
and
Yeah, exactly.
as I'm
Exactly.
saying that.
Maybe that's why we even start with itself.
You said?
I see. Maybe that's why we even started with the binomial.
Yeah. It's bringing more point. Thank you very much. Thank you, Kendi. Osaho, I didn't
Is
hear
it?
your voice all throughout. But thank you, everyone. So
All right.
see
So,
you next class. You said?
all right. So,
Hmm,
yeah, that's on. That's on.
okay.
So we'll refer back to the dedicated drive for relevant materials and tutorials and exercises. That's for reference.
I thought you said you're sending them again, is it?
Yeah, I'll send them again. I'll send them
Okay.
again in the
Thank
WhatsApp.
you.
This I'll send
Thank you
tomorrow. We
very
expect
much.
them.
God bless you. Bye,
All right.
everyone. Okay.
Thanks for listening. Have a great day. Bye.
And you too. Bye.
Bye.
Yeah, bye.
All right. Bye. Bye.